more skeletal structures. Advanced edition. Advanced. So first off, let's just change this skeletal structure to a condensed structure, just so that we can do that, I'm just going to draw this to say it's equal to, so essentially take a minute to do that yourself, and then come back and we'll do it together. All right, you're back. So I'm just going to draw the circle part. There are 1, 2, 3, 4, 5, 6 different positions in that hexagon. So each of those 6 positions has to have a carbon atom. Because these carbons have 2 bonds to other carbons and they are neutral, we have to assume that they have the number of hydrogens that would make them neutral. So that would be a CH2, CH2, CH2. This would be a CH2, CH2. This guy here, which is that one there, has 3 different bonds to carbon, so we're going to draw another bond to carbon here, but it must have another hydrogen itself, because that would give it its 4 bonds. And then here we have a CH2 and a CH3. So that would be converting a skeletal structure to a condensed structure. Okay, so that was kind of similar to what we did last video, not really advanced. The new advanced thing is with this asterisk. And again, this is kind of the hardest part of skeletal structures. We have to infer the presence of electrons and hydrogens based on formal charge. So, for instance, what if we had the same type of molecule? We'll just draw. Let's just draw that. So we have a 5-carbon ring, right? Because each of those points is a carbon. So we're going to have a carbon, bonded to a carbon, bonded to a carbon, bonded to a carbon, bonded to a carbon. Let's just first tackle all of the atoms that have no charge. So this carbon here has no charge, so it must have 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens. Again, those have 2 hydrogens because each carbon, if it's neutral, needs to have 4 bonds. So 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds. What about this negative charge here? Well, how would a carbon get a formal charge of -1? Carbon's group is 4, so -1 equals 4. So that's its number of valence electrons, minus, essentially, this number has to be 5, right? 4 minus 5 is -1. And we know that the formal charge on that position is -1. So how could that be? Well, for this to be 5, what if we had 1 hydrogen bonded here, and that was it? Well, then 4 minus, it would be the number of lone pair electrons, which in this structure right now is 0, and then we add the number of bonds, 1, 2, 3. So 4 minus 3 is +1. So it can't be this, right? It can't be that the carbon just has 1 hydrogen. It has to be something else. Well, what if that carbon had that hydrogen, but it also had a lone pair? Well, in the formal charge calculation for -1, it would be 4 minus the lone pair electrons. So that'd be 2 plus 3. So 4 minus 5 does equal -1. So this structure that was amazing in the sense that it took us no time to draw it, and we just put a little minus charge right there, it infers that that negative charge means that it has just 1 hydrogen and it has a lone pair of electrons. So that is the power of these skeletal structures. They really just speed up the process of us being able to discuss and talk about organic chemistry. So what about if we had another skeletal structure? We'll just do one like this. Shoot. Never mind. I guess it really is just carbons that. Yeah, we'll do another one. So let's do. Oh, that was too similar to the other one. Okay, we're just going to convert this skeletal structure into a condensed structure, I guess. So yeah, convert that into a condensed structure. So take a minute, give yourself time to do this, and then pause it and do that. Now you're unpausing. So if I was going to convert this into a condensed structure, and actually we'll do both condensed and we'll do the Lewis structure, but the condensed structure would look like this. So CH3, there are two different CH3s there. This is a CH3, that's a CH3, so there's two of those. Then we'd say C plus for right there. And then this is a CH2 and a CH3. So that would be the condensed structure for that for that structure right there. What would the Lewis structure look like? It would be a CH3. Man, this is going to take so long. CH3, CH2, CH. Oh man, I almost did a condensed. So that's what the Lewis structure would look like. So that positive charge implies that there are no hydrogens there and there are no lone pairs there. To convince yourself of that, do the formal charge calculation for that carbon atom, and you'll see that it is positively charged. All right, we did it. We can now draw organic molecules the way that we want to, and it's great. All right.